The second part of the speech production process is the shaping in the vocal tract. The vocal tract is in fact a tube-shaped cavity with a variable cross-section area which acts as a resonator, so it is able to amplify certain frequencies from the excitation signal and attenuates other frequencies. So it puts a kind of envelope over the spectrum of the excitation signal. The maxima of this envelope are called the formants and the minima are called the antiformants. The maxima are the ones which contain most energy of the speech signal. And as we have seen in chapter 2 of this course, such a structure can be represented as a linear time invariant system. Here there are different possibilities. In common practice we prefer possibilities where we have poles only in the equation of the linear time invariant transfer function. Physically, this can be described by a tube of variable cross-section, which is approximately 17 centimeters long from the glottis here to the tip of your lips. At the lower end, at the glottis, there is a structure behind, so there's a sonically hard ending. And at the upper end, when you open your mouth, when you speak, the airflow can evaporate, so we have a sonically soft ending at the upper end. This information is important if we want to model the human speech production process, as we will see later in this course. In parallel to the oral cavity, we can also link the nasal cavity via the velum, which is inside your cavities. Now we will have a further look into what happens outside your head when the sound signal gets out of your mouth. There you also have a certain transfer or radiation characteristic. And what you see in the background on the left-hand side is a cut of the horizontal plane, and on the right-hand side a cut through the vertical plane in this direction. And you see that the directivity of the speech signal is much more pronounced for the high frequencies. That is, for high frequencies you have a further production of the speech signal, radiation of the speech signal to the front, whereas the low frequencies are more surrounding the head. This is something you can even hear when you listen to a person which is not directed towards you. We'll now have a look into the characteristics of the speech signals which are produced that way. And on the first slide we see two representations of the speech signal, either in the temporal domain or in the frequency or spectral domain. On the left-hand side of those pictures you see the excitation signal only, which is then shaped through the linear time invariant filter, which you see here. And on the right-hand side you see the time sequence and the spectrum of the resulting speech signal. I have put it here in two different examples. The first one is a periodic excitation signal, which you see here, the impulse train. And the second one is this noise-like signal, which you see here. The impulse train has as a spectrum also an impulse train, because the spectrum of an impulse is flat in frequency, and the spectrum of a periodic signal is a line spectrum, so it needs to be a line flat spectrum, which is an impulse train again. And the spectrum of this noisy signal is flat, it's a white noise, but continuous, so it contains all frequencies. If you put such a signal through the vocal cavity, here, the linear time invariant filter, you get the speech signal at the output. And this is either a periodic one with a time period which is the inverse of the fundamental frequency, or it looks like a noise-like signal, but still it is shaped in some way, which you can see when you look at the spectrum. So you see that there is an envelope put over the spectrum of the excitation signal, with the maxima corresponding to the formants and the minima corresponding to the antiformants. The maxima are a little bit more pronounced for the periodic excitation signal because this is produced down here. So you have a relatively long way through the vocal cavity, whereas for the noise-like signal, this is produced more to the front, so you have relatively few space for shaping the signal. This is a one point in time look at the signal. And if we speak, of course, we change the positions of our articulatory organs. That means that it would be preferable to have a look where we do not only have the amplitude and the time as variables, but also the change over time. So we need a quasi three-dimensional representation, which you know from the second chapter of this course. It's called a spectrogram. And what you see here on the lower panel is the spectrogram of a sentence of speech. And on the upper panel, you see the corresponding time signal, the amplitude over time. So on the x-axis, you have the time. On the y-axis, you have the frequency. And the amplitude is actually illustrated through the color. Reddish colors mean more energy at a certain time and frequency, and blue and green-like colors mean less energy at that position. You can now try to read such a spectrogram. For example, you will detect these lines here, which are repeated in the frequency range. And if you count well, you will detect approximately 8 lines until a frequency of 1000 Hertz, which means that these lines correspond to the fundamental frequency of 125 Hertz. So these have a distance of 125 Hertz, which also says to you that this is the speech signal of a male speaker. You can even see the more reddish areas here and here and here, which correspond to the formants. And you see that those formants change over time as we articulate. You also see some parts of the signal where you have sudden start from more or less a pause. This happens, for example, if we have a B or a P sound. And you also see some parts where you have more energy in the upper frequency area and you do not have a periodicity here, which correspond to the fricatives like a F or a S sound. So you can actually read such a spectrogram and try to identify the corresponding sounds from it. Another interesting illustration is the distribution of the amplitude if you analyze long sequences of speech signals. These are the amplitudes which you can measure at the output of the microphone. And if you do that, you will find out that the most probable amplitudes, here's the probability which is shown, are the ones which are very close to the zero, whereas the probability drastically drops for the higher amplitudes. That is, that most of our speech sounds actually consist of silence or close to silent amplitude parts. This distribution of the amplitude is interesting and important if you want to code or to store speech signals, because those amplitudes which are more frequent will usually be coded in a more precise way, whereas the ones which are less probable will be coded in a more rough way using less bits, which also influences, of course, the transmission bandwidth which you need in order to transmit such a speech signal, for example, in telephony.